All right, thank you. Yeah, so today I want to talk to you about when and how we use confidential computing at Signal Messenger. I'm going to start with a little bit of, well, let's see. There we go. All right, wrong button. Start with a little bit of background. I know a lot of you out there are already familiar with Signal Messenger. Some of you have even written papers about some of our systems, and thank you for that. But for those who aren't so familiar, Signal Messenger is the world's most widely used, truly private communications app. Okay, a lot of apps have great privacy features. I need to be clear about what we mean here. When we say private, we mean that we're protecting both user data and metadata. We protect message contents, of course, but we also protect information about who's connected with whom. And we protect this from everyone, including ourselves. We do not ask you to trust us. We back this up with by making sure we do everything in a transparent and auditable way. Our code is open source. Our protocols are well documented. We've received extensive scrutiny from the information security community. Now, almost everywhere through our app, we're able to do this using cryptography to ensure with mathematical proof that no sensitive data leaves a user device. And this is a great thing. It may seem hard to build a feature-rich app this way, but here's some examples of how we do it. The Signal protocol, really our starting point here, developed by Moxie Marlinspike and Trevor Perrin, protects our message contents. And this has had an impact far beyond Signal Messenger. It's used by WhatsApp, Facebook Messenger, Google, and more. Key to protecting metadata here is our sealed sender system. It uses a combination of encrypted envelopes, delivery tokens, and sender certificates to shield sender identity from our servers while still giving us the tools we need to combat abuse. One of my favorite bits of technology is our Signal private group system. It's an anonymous credential-based system that protects information about groups and group membership from our servers. And more. Basically, whenever we design a feature, we build it in a way so that only people who can know something are the people who should know it. Now, the examples I just gave were places where we have this mathematical proof that sensitive data is not leaving a user device. When this is the case, you don't need to worry about what is happening on our servers. Our servers are simply shunting around opaque blobs of data. This is not a world where we need confidential computing. But that's not the whole story. Because what's going to happen when there's a feature that we would like to offer our users, but we cannot find a purely cryptographic solution like this, where the only way we know how to implement it involves having some sensitive information leave our client device? Well, this is going to be a big change for us, so we need to think carefully about it. And this needs to be analyzed on a feature-by-feature basis, of course. But there are some things that we can say in generality. The first thing we want to do, this is a big change for us. The core of our application doesn't have this property, right? It's protected cryptographically. So we do want to make it optional for our users to be able to opt out of it, even though we will stand behind any feature we offer, of course. More to the point for this conference, though, is we need confidentiality, right? This sensitive data leaving the user device must be protected, so it must go to a server where nobody can learn about it. And by nobody, I mean even an attacker with full administrative and physical access to the machine, able to carry out sophisticated side-channel attacks. Okay, the first two, the optionality and the confidentiality, are meaningless unless we have attestation. The client must know what server the information is going to, that it is up to date, and they need to know what code is running on the server to process it. Putting this together, we see that any solution we provide that involves sensitive data leaving a client device must involve sending this data over a secure channel into a confidential, attested, trusted execution environment. Confidential computing is essential. It's not enough on its own, though. So to make this concrete, I'm going to take the time we have left to dive in some detail into one of the two systems we use that are backed by confidential computing today, and this is our contact discovery service. So here's the feature that we want to offer our users. We want you to be able to figure out which ones of your contacts are also Signal users and fetch some information about them so you can set up a secure connection with them in our app. Simple enough, and certainly we're not the only messaging app that does this, right? And the standard thing you can do here is to create a secure channel to a database, send the phone numbers over that channel, and then the database processes them in the clear, sending results back to the user. That's fine. The secure channel is important and provides necessary protection, but at the end of it, this database is still saying, trust me. Trust me not to log anything. Trust my administrator not to record the queries as they come in. We don't do that. We don't ask you to trust us. We need a different way. Okay, so now our challenge is clear. We need to find some way to match your contacts with our database in a way that our DB admins can't learn anything about it, in a way that even this attacker with full access to our machine can't learn anything about those phone numbers in your contact list. Well, it turns out there is a family of cryptographic solutions here called Private Information Retrieval, or PIR. It comes in two basic flavors. Information theoretic PIR is pretty efficient, but requires multiple non-colluding servers. That means that we can't operate all of our servers. We need other parties at arm's length to be operating some of the servers for us. This is an operational and legal challenge. In the end, it really comes down to reliance on human claims of non-collusion. I think there's a lot of great progress. People are working hard to make systems like this work. But for us today, we don't see this as workable. Hopefully in the future. We also have cryptographic PIR, though. This doesn't require the trust, but is considerably more expensive. Just to give you a ballpark of the costs we'd be looking at, a recent proposal, Frodo PIR, very helpfully put concrete cost estimates in their paper. So I'm going to use this. Okay, and using their numbers, it looks like it would cost about a penny for us to process a typical contact list of 1,000 phone numbers. Seems pretty cheap. But what if you want to process 100 million of these every day, right? This adds up fast. We're looking at a cost of $365 million a year. This is orders of magnitude beyond what we can afford to run this service. This does not seem viable to us. Now, with good engineering, can we bring these costs down? I'm sure we can. Is Frodo PIR the best system suited for our use case? Perhaps not. There are other PIR systems out there. We're actively evaluating them, and we would love to go to PIR when possible. Again, it's something that doesn't seem feasible to us today. So what are we going to do? Well, as I said before, any solution, now if these phone numbers are leaving your device, they have to go over a secure channel into a TEE. And the easiest thing we can think of is to say, hey, we know how to build this system with a database. Why don't we just lift and shift our database into the TEE? And this is as simple as it sounds. This is really a great solution, right? And this sort of lift and shift solution is going to meet many potential confidential computing users' needs. Let's look at it. The first thing, now only the TEE can read these phone numbers. My attacker with full access to the machine, I don't care if they have interposers on the DIMM and can read the physical memory. They're not going to be able to read these phone numbers in the clear, right? Fantastic, not just good is attestation. We actually know what code is running on the servers, right? You can't sneak any logging in or anything like this. It will be detected, right? So this is a really good start. Unfortunately for us, there's a real barrier here, and that is that databases are going to have side channels. Different queries are going to access different memory addresses. An attacker can run their own queries, observe these patterns, watch your queries come in, observe those patterns, and learn a tremendous amount about what you are doing, even though they don't break the encryption. And this makes it clear that we must, if we're going to offer this service, we need to find a way to build a side channel hardened database that operates in TEE memory. So this is what we did. It turns out that hiding these access patterns at a small scale is fairly routine. There's some linear scans and oblivious access idioms you can use, but they don't scale well, and we need to operate this at database scale. So we turned to the oblivious storage research, where there's a great wealth of ideas, many of which we're still exploring, but 3 papers in particular gave us tools we needed to put our system together. These are PathoRAM, Oblix, and Snoopy, and I'm going to talk a little bit about each one as we get an overview of how we built this database. Our foundation is something called oblivious RAM, or ORAM. And what this does is it shuffles around page-sized memory blocks on each access in a way that's untraceable. So that way, every time we access a page at a given logical address, it gets a new physical address. An attacker observes the physical addresses, but learns nothing about our logical access patterns. We do this using a combination of patho-RAM, which gives us a basic strategy of shuffling things around, and Oblix gave us tools to make sure that we performed all the shuffling in a way that was free of side channels. On top of that, we need to build an appropriate data structure. We settled on an oblivious hash table with linear probing and Robin Hood placement that minimizes the maximum displacement of our data from its target. This lets us provide fast, constant time lookups. Finally, we needed to do some sharding. Oblivious RAM, the patho-RAM we're using, required single-threaded access. And we're going to be operating on machines that have many cores. We need to use these resources. Turns out if we shard in a naive way, scattering the queries to the shards and gathering them, we are going to leak information. We need to do this carefully. This is where Snoopy came in. They provide methods to perform this scattering and gathering in a way that is also free of side channels. Putting all this together, we now have a system that is free of timing and memory access pattern side channels. Combining that with the promises of the TEE, we're using Intel SGX. We have a high level of confidentiality. We have workload level attestation, thanks to SGX. And we have optionality because you can always choose not to share your contacts with us. This meets our needs. And this really does perform too. Just some benchmarks we run here for a database of 100 million 56-byte records on a 16-core SGX-enabled Ice Lake processor hosted at Azure. We can run a real workload. This involves not just the lookups, but noise protocol handshake negotiation, our rate limiting logic, and all of this. This is our production system running 76,000 lookups per second, 125,000 inserts per second. So what we see putting this together, a powerful confidential computing hardware that's available today, combined with recent research and a little bit of careful engineering, enables even an organization with very stringent requirements like ours to provide a secure, economical, global scale service right now. Confidential computing is really enabling like a new level of security and transparency for our computing infrastructure. It's letting us provide services like contact discovery today. I'm really excited about the things it's going to enable us to do in the future, especially as we look towards a multi-cloud, multi-hardware future. But I'm most excited about seeing what some of you guys out here are going to do with it too. So with that, thank you.